All right, so what were we talking about last week? What was the circuit that you guys made in SPICE? What was the
RC.
observation you made? Did you look at your
RC.
notes?
There was an observation. What do you mean?
Okay. What was the purpose of making this circuit? Made this circuit, right?
I need a voltage.
So there's a capacitor, and this is a current source, right? And when we made this circuit in SPICE and simulated it, right? What did we look at?
The voltage and the current. Very
There's a
good.
current, right? So the current, we set the current to be a sine wave, 100 hertz. Right? So then when we looked at the current waveform, it's a sine wave, right? So it starts at 0, goes to its max, comes back to 0. So then, now, this current is going through the capacitor, right? Normally, if I had a resistor here, and I'm pushing this current through it, the voltage across that resistor, what would it look like? Right? If I'm pushing a current, a current that is a sine wave, it would be the same, right? Because why? Because V is equal to IR, right? So this current, if it looks like this, it just gets multiplied by R. So the only thing that probably would change is the magnitude, right? So then the voltage would look the same. But in this case, we have a capacitor, right? So if you want to find the voltage across the capacitor, what do you have to use? In the case of a resistor, you use the resistance. In the case of the capacitor,
1 over.
right, what is it called?
Oh, impedance.
Impedance or
Very good,
reactance.
very good. These guys are listening.
So,
We did ZC.
but what is ZC equal to?
1 over LC.
1 over,
Oh. Something.
It's like some Greek letter, right?
Is it a Greek letter?
well, what is, okay, well, there are 3 terms here. Which one of them are you sure about? This is
C.
C. Okay, so we definitely have a C
Good.
in there. We also know that the impedance of a capacitor is what kind?
Complex.
It's
J.
So you have a J
Omega.
omega
Very
because
good.
it's
You guys have been
frequency
listening.
dependent,
I can't believe it.
Okay.
right? The
Yeah, there's a big
impedance
difference.
of a capacitor is frequency dependent. It
Okay.
changes with frequency, right? And we've talked about this. If frequency is 0, what would be the impedance,
1 over 0.
which is
Infinite.
infinite, right? So if I want to push a DC current through here, once the capacitor gets charged,
It stops.
it stops. There's no more current going through, right? And as the frequency increases, goes to infinity,
It gets smaller.
becomes 0. Okay, so then,
Then it's just like a line.
so if I want to now find the voltage across the capacitor, VC, using that, so I have I times this ZC, right? Which is 1 over J omega C. Right? And normally we like the J to be on the top. So if I multiply this by J over J, right? J over J, then I get a J on the top. Let's just put it here, I over, and then here, J times J, omega C, so I get negative J I over omega C. Right? So this is my voltage across the capacitor. Right? And then we said, okay, I wonder what this is going to look like. And that's why we went and did the
Oh yeah, and then
simulation.
it was in front.
And when we did the simulation, we realized that it went like this. Right? That the voltage was lagging the current. So this is the voltage VC. Of course, it doesn't, when you look at it continuously, it's like
Yeah.
that,
Yeah.
right? So this is that's VC and this is IC, and then we asked why? Why? Why does that happen?
Because it has to charge.
Right, so physically, intuitively, if you think about it, is that when the current is going through the capacitor, as the current is increasing, right, it's charging the capacitor,
Yeah.
right? Let's start looking at it at this point. This part of it gets a little bit confusing, but when the current is at its max, right, the capacitor is still charging, right? Because this current source is just pumping current through, right? So the voltage hasn't reached its max yet. When the current finally stops, right? When this is not pumping any more charge, that's when the capacitor is fully charged, right? So the voltage across the capacitor is at its max.
Wait, how do you know it's fully charged? What if it didn't get enough?
So because you're thinking of, in this case, you have to think about it, what the current source is doing. The current source is the one that is pushing the charge through,
Should.
right? The current source is the one that's pushing the charge through. So once the current source says, I'm done pushing charge,
Oh, that's as much as it
that's as much, that's the maximum charge that you're going to have on the
Or
capacitor.
not like the maximum charge that the capacitor
No.
can handle?
No.
Oh, okay.
Right, the maximum charge the capacitor can handle is based on its voltage rating. Right, remember how we blew up a capacitor?
When you said maximum on the capacitor,
That's the maximum that this capacitor is going to have for this circuit, right? So the current source is pumping charge through, right? And once it's done, once it goes to zero, that's when you have the maximum charge stored on the capacitor, right? So that's when you get the maximum charge. Now the current starts going the other way, right? It's going negative, so it's flipping. So now it's going to take away charge from the capacitor, and it's taking the charge away, the voltage drops, right? Because the current is going the other way. So then, as the current becomes more and more negative, right, the charge leaves the capacitor, the voltage drops down to zero, and that's when the current is at its max, and then it charges up the capacitor again the other way, right? Now the charge is going the other way, so now the voltage is negative, and again, when it reaches zero, that's when the charge on the capacitor is maximum negative, and it keeps repeating it. So that's what we observed. That's what intuitively makes sense. Now we want to come back and see if the math makes sense. Is the math going to show the same thing? Well, we look at the voltage across the capacitor given by this equation, right? And when we look at this, remember we talked about the complex numbers, there was a magnitude associated with it and there was a phase associated with it, right? So what is the magnitude? The magnitude was, when we say magnitude of a complex number, it's equal to the real part squared plus the imaginary part squared square root, right?
Oh, okay.
So what's the real part of this?
you don't have.
Zero.
Oh, it's just that.
What's the imaginary part of this?
That.
This, right? So I squared over omega squared c squared, which is just I over omega c. So if I want to find the maximum voltage across the capacitor, I have to find the maximum current that is going through it, and then divide it by the frequency, in this case was 100 hertz, whatever that frequency is, times the capacitance, C,
So,
right?
what is the capacitance on this one?
So let's say, I think in the simulation we set it to, what was it, 100 microfarad? Or 1? 1. Sorry, 1 microfarad. Okay, so 1 microfarad, right? So if I want to find maximum voltage across the capacitor, right? So VC max, it would be IC, wouldn't it make sense that it's the maximum current, right, divided by the frequency? Well, omega is 2 pi f, frequency being 100, times the capacitance, which is 1 microfarad, right? Maximum voltage using maximum current, which intuitively, when you look at it, or when you look at the waveform, like you go, what? To find this maximum voltage over here, I take the maximum current, right? I make that measurement, then I put it in this formula. That's going to give me the maximum voltage over here.
Weird.
Weird. So why? Why is that? So we looked at the amplitude. This is what it is, right? Now let's look at the phase. How do we find the phase of a complex number? So the phase of VC, do you guys remember the phase of a complex number? It was the inverse tangent
Oh, yeah.
of the imaginary part
Wait,
over
what
the
it
real
was?
part.
I don't remember what tangent is.
Tangent. So if you have a right triangle,
Oh, yeah.
the
Opposite
tangent
of
of this angle is the opposite over the adjacent.
An inverse tangent gives you.
X over Y.
So if I give you the tangent value and you take the inverse tangent,
Oh,
that
that
will give you the
makes
angle.
sense. Because it's that, and then
Wow.
it's genius.
It is genius. Math. It actually works.
This is
Okay,
this
so
is so cool.
in the case of the voltage,
Oh, wait, what does a triangle have to do with this?
Because you can grab
the
it.
tangent
on
is,
the
so
imaginary.
I'll show you, remember the unit circle?
Yeah.
I'll show it to you in a couple of minutes. But so what is the inverse tangent? So what is the imaginary part of this?
That.
The entire.
It's just I over omega c, right?
Isn't it
What's the real part of it?
No.
Really? What?
0.
Or 0.
0.
You look
So
Wait, why is it that non-negative?
what's the inverse tangent of this? This becomes infinity, right? Well, not defined,
Yeah.
but
Why is that non-negative?
which one?
I or W?
Oh, yes, you're right. Oh, negative. Thank you. So, negative.
Good catch.
Yeah, thank you. So, what angle do we know whose tangent would be infinite? Look at this. Tangent is opposite over adjacent. When would the tangent be infinite?
They're the
When it's a
same.
straight line.
Which means the angle is 90.
Oh.
And in this case, since we have a negative, it's negative 90. When adjacent is 0, so when this gets closer and closer and closer, which means that this guy is going higher and higher, which means that the angle is becoming 90 degrees. Okay? And so,
You follow that, Peter?
Yeah.
so if you look at the complex plane and the unit circle, this is the real axis, this is the imaginary axis, right? And if I have this complex number which has this real part and this imaginary part, this is the angle, right? When I don't have a real part, it means that my number is here. My complex number is here. I have only imaginary part, no real part, and the angle is 90.
Okay.
And when it's negative, right, the imaginary is actually this way. So in this case, the magnitude of this is I over omega c. It's only on the imaginary axis, and so the angle is negative 90.
Okay.
Call it what?
No.
270?
Well, you know it's
It
gonna
could be. It is. It could be. But, and you're right. If I look at this sine wave, this is the interesting
Oh, it's
thing,
shifted
right?
this way.
Yeah.
But
Depends
that
on which way you look at it.
Oh,
So
that's
if I look at it
Very
this
good,
way, I
Armand.
say it's 90 degrees behind because it happens later in time,
Or-
so 90 degrees behind. Or if I were to draw the rest of this, it's 270 degrees ahead,
Whoa.
That was good. That was good.
right?
Good job, Armand.
And so I asked you guys to actually go ahead and measure these times, if you remember.
Oh yeah.
And then when you plugged in the numbers and then you looked at this difference
90.
over the entire period, this turned out to be the period divided by 4. One full period divided by 4. Well, one full period divided by 4 is 90 degrees. So when you actually made the measurements, you see that it's exactly 90 degrees behind. It's lagging by 90 degrees. Lagging, it's behind, right? It's like when you're running and somebody's not catching up with you, they're lagging behind you, right? So it's lagging by 90 degrees. And if it was the other, and if you look at it the other way, it's 270 degrees leading. Right?
Wait, so which one's first?
But in this case, physically, right, when you look at it, what's actually happening, it is the voltage is building up, right? So it is actually lagging. As the current has reached its maximum, but not the voltage. And it doesn't reach its maximum until the current reaches 0, so that the voltage is actually lagging.
Okay, so the current is in front of the voltage.
Right. So this is what we did in simulation last week, right? And then, now you guys are going to actually build a circuit and see it, right? Because, hey, I did simulation. Well, who knows that the software is doing the right thing? Let's actually build it. Let's look at the physical thing and see if it actually does the right thing. Now, when we build the circuit, usually we don't have current sources. There might be current sources out there, I'm sure there are, but usually we work with voltage sources, especially this guy that generates the sine wave, it's a voltage source, right? So there are two ways of doing this. One way is that if I put a resistor here now, right? And if this resistance, because I need you guys to pay close attention to this, if this resistance is much bigger than the magnitude of my impedance of my capacitor, right? When I look at the current, if I look at the total current going through here, first of all, what is the total current going through here in terms of these two components, right? So if I use, again, Ohm's law, right? My current would be equal to, sorry, you know what? Let me redraw this because here I'm still working with the current source. I'm trying to replace it with a voltage source. So I'm gonna erase this, and now I'm gonna have an actual voltage source in, and then I'm gonna put a resistor here and a capacitor like that. Okay? So if I want to find the current going through here, right, using Ohm's law,
I equals V
I
over
is
R.
equal to
V over
V over
R. Z. Z. Oh,
right, they're in series, right? So I
R
want V
plus-
over R plus Z C, right?
Yeah.
But then if R is much, much bigger than ZC,
Then it's.
then this is approximately V over R. So I can treat this as my current source.
Why?
So
Because,
it's like a black box.
because right here, the I will be set to V over R as long as
Oh!
this CC is smaller, right?
So we need to make.
So if I did this,
So
then you guys can just go look at the voltage here, knowing what this resistance is and what the voltage is, what the current is, and then go through the same calculations and figure out what capacitance is.
Genius!
Okay?
Wow.
As long as R is much, much greater.
As long as R is much, much greater. Now, the way I'm asking you to do it is actually a little bit different because I also wanted to show you this other aspect. So let's say this R is not much, much greater.
Oh.
Okay. Then I have to deal with this, right? Or if I'm measuring the voltage here, VC, which is what you guys are going to be doing, we're going to need to do that anyways. We're going to have to measure this VC to figure out what the capacitance is. Then what is I? In that case, what is I?
Wait.
If I know VC,
I is VC over.
this current through the resistor, use Ohm's law.
It's the same.
It is the same. It is the same, but I can also find I as
Oh, VC.
the voltage across the resistor divided by the resistance, right? What is the voltage across the resistor?
VN.
V in
Minus VC.
minus Vc divided by R. So if I do this, I'm actually finding the exact current, right? And I don't have to make this R much larger than ZC. I can put any R I want. I make the measurement, I find the current, okay? Once I have that current, I'm gonna find, so the task is, we wanna find the capacitance, right? So once I have that current, let me see actually if you guys can figure it out. We said, what I just erased, VC is equal to Ji over omega C, negative, right? And the amplitude VC was equal to basically I over omega C, right? I want to find C. I want to find the value C. How would I do that?
You mean like isolate for C?
Mm-hmm.
Oh.
So
Find-
solve for C,
Yeah.
right? So C is equal to
VC
Just multiply it by
VC
omega
omega
over I.
over I, right? And then omega is 2 pi f, VC I 2 pi f, right? So if I know the frequency, if I know the current, if I know the voltage, I can find my capacitance, right? And so, and then to make it easy, what we just said, I'm going to take the max voltage as my magnitude over the max current, and then multiply by 2 pi f, and then I can figure out what my capacitance is. Okay, so in the lab that you're doing, you want to measure current, you want to measure the voltage, so you're going to see waveforms like this. You look at the max, plug it into this equation, and find what the capacitance is. And you're going to do that for multiple frequencies. Okay, so you're going to measure that capacitance for multiple frequencies. Do you expect it to be the same or different?
Same.
It should be the same, right? It's the same capacitor, right? And then you take an average of those over the different measurements and see that that's going to be the capacitance value. Okay, so that's what we're doing, right? And the way I have you do it, we could have put a large R here, and then just use this V over R, V in over R. Okay, this would have been V in over R. I could have done that, or what I'm asking you to do is to do this, V in minus Vc over R. And to do this V in minus Vc, you're putting a probe here. I'm actually putting a probe here. I draw my probe. Right? I'm putting another probe here. Right? And then you use a math function on the oscilloscope that will tell you Vn minus Vc. Right? You measure that, you know the resistance, you can find the current. You have Vc, you plug it all through this, and figure out what your capacitance is. Yeah.
Oh, okay.
Because what we did is
Yeah.
we brought this one here, and so that's 1 over C.
Mm-hmm.
Thank you, Rick. And so we carry it through here, so therefore C is actually the flip of that.
Yeah.
I over VC to pi F. Okay, and that's what we have in the table. That, as you guys observe, as the frequency goes higher and higher, the voltage across here drops. And so if you look at this voltage compared to this voltage over frequency, if I were to plot that, this would look like this. So there is a certain frequency which is called the corner frequency or the cutoff frequency, after which all the voltages are going to get cut off.
It doesn't have enough time to charge up.
Oh wow. Yeah.
Right? So that becomes a filter.
So
Okay.
if you want to cut out the higher frequency, or you just make it higher.
You figure out what this value, and this value is actually 1 over 2 pi over RC. Okay? So using that, by changing these values, you can make it, the frequency
Okay,
higher or
guys,
lower.
this is called a low-pass filter.
Yep.
It's called a low-pass filter, use it all the time.
All right, guys, so any other questions on this? So wasn't that cool?
Yeah.
You actually saw a capacitor was causing this phase difference, right? So to take this further, naturally, we looked at a capacitor. We're going to look at an inductor. Right? So if I replace this now with an inductor, right? Again, I have my current source, I have my inductor, and I want to look at the voltage across the inductor, right? So if we go through the same thing as we did here, so first of all, to find the voltage across the inductor, VL would be the current IL going through the inductor times Z
You change the Z.
sub L, right? And what is Z sub L?
J
What's the
omega
impedance
L.
of an inductor?
J omega.
J omega L. Right? Okay. So if you look at that, VL now is equal to IL times J omega L. Okay. Right? Is that a complex number?
Yep.
Yeah, it's actually, it has only the imaginary part. The real part, again, is 0. So it's an imaginary number, right? So what do you expect to see if we go ahead and simulate that circuit? What do you expect to happen here? If our current looks like this again, it's the same current source.
What would we shift it, Austin?
Yeah, the current will be in front, and the or just flip positions.
So the voltage is going to be ahead.
Right.
Wow.
Does that intuitively make sense? Why would that be?
Because
Can you explain it
inductors are
physically?
the opposites of capacitors.
They do that, right? Whatever the capacitors do, the inductors do the opposite. But why? Why is that?
Why not?
So, if this was a philosophy class, I would take that answer. This is an electrical engineering class. So, as the current is building up, as the current is starting from zero and it's building up, this is where it's changing the fastest. And inductors, what do?
They don't like change.
They don't like change.
Very good,
Right.
Ron.
They are going to oppose that change. This inductor is going to oppose that change. So how does it do it? By putting a voltage across itself that is the opposite of what's supposed to happen. So you get the maximum, what color should I use? Purple?
Purple.
Purple or green?
Purple.
Purple, okay. So here we're going to get the maximum voltage across the inductor, okay? But then as the current starts building up, the magnetic flux around the inductor gets built up, and that voltage starts dropping. The change becomes less and less, right? That curve is becoming smaller. The change through the curve is smaller and smaller, so the voltage starts dropping, right? And so the voltage drops down to here. So by the time the current is at its max, the magnetic flux is at its max, the voltage across the inductor is zero. And again, when you look at the max of this curve, it's flattened, has flattened out, which means that it's not changing, right? If it's flat, the current is not changing as fast. So the inductor is not going to oppose it as much, and that's why the voltage is at zero.
Are we gonna do this in space?
Yeah.
No.
So then it just continues doing, right? As the current starts changing the other way, it wants to drop. The inductor doesn't like it. It says, I don't want you to drop. So it's going to actually try to push. It's going to try to keep the current going. So the voltage becomes negative. It goes to its max
That's crazy.
when now the current,
So it's 90 degrees
The
in
other
the front?
right, it's leading. And look, J, it's not negative. It's a
Oh.
positive J value, so it's up here, so you get a plus 90 degree.
That's weird. Can you draw the rest of the time?
Okie dokie.
Or it's behind 270.
Yeah.
Like that. Oh!
Change colors.
Like that.
Nice sideways.
That looks like DNA.
The helix.
It does.
Plus
Coil.
an extra little
Okay.
orange thing.
Let's go simulate it.
Yes, sir.